Okay, good morning everyone. Assalamualaikum. And let's jump straight into the lectures. Been postponing quite a few. So, okay, today we are looking at, I think we started a little bit, but was not quite prepared at the time. So let's look at it again. So one considers the case of the hydrogen atom, or much more generally a one electron atoms. Okay, normally it's called hydrogen light atoms. And just like in the case of your Stark effect, so you have an electric field, but instead of electric field, now you consider the case of magnetic field. Okay. So if you have done some form of atomic physics or somewhere along the line in modern physics, or you probably have heard about Zeeman effect, which is essentially a splitting of the spectral lines when the atoms are actually put inside a magnetic field. Okay, so we're going to study this using perturbation theory. So one of the things that we have seen before, probably in a different course, I suppose, we can have your magnetic field and also your electric field be described as in terms of potential. Okay, so for the case of electrostatic, electric field is in terms of a electrostatic potential, scalar potential, but for magnetic field it's actually given by vector potential. So and the vector potential can be given as follows. Okay. And essentially when you remember, if I'm not mistaken, this would relate to your expression, the one that we have seen earlier or somewhere in naturalism. Okay, so one can actually invert this equation to this following equation. Okay, so what we're going to do is we're going to fix your B to be pointing in a particular direction. So normally it's taken to be your Z direction, and then you can substitute this inside your vector potential over here, and then this can be sort of calculated out to be the following, where you have your X component there and your Y component there, with your B multiplying the respective components. Okay. So one of the things that, yeah, I'm not quite sure where this is precisely introduced, but probably in the first course you might have come across that sometimes you can actually replace your momenta operator. Momenta operator goes to a modified one. Okay. But you have a function over here. So let's say there's function f. Okay. So and this kind of modification still respect the commutation relation. So this is, if I want to do this in 3 dimensions, I will have your delta ij here. So I, j, delta ij. Okay. So precisely because of this reason, meaning you can actually modify your momenta operator by a particular function, one can actually essentially when you do this substitution inside your consider the what you call the momentum operator together with contribution from your vector potential, one can actually find that this momentum operator gets replaced by the following. In some sense, this is actually representing some kind of your magnetic field contribution into your momentum. Okay, I'm trying to explain this in a better way, but essentially, if you have the full theory, this part will actually contribute to what we call the there will be an extra term, okay, which is not considered here, of course. There will be an extra term that talks also about the electromagnetic field momentum. Okay, but here you thinking of your magnetic field as just a background field. Okay, but okay, never mind. I mean, the idea is essentially this kind of substitution still obeys the ordinary canonical commutation relation. There is a condition, I can't remember precisely, but no, the idea is just simply that. Okay. So if you plug in, remember your Hamiltonian is essentially given by this, okay, plus some potential. Okay. So if this is now going to be replaced by that, okay, or this one, okay. Now again, I think in the later chapters I've started to ignore putting a hat on each. So this is actually an operator. Okay. So if you substitute this what you call modified momentum into your p squared over here, so you get your ordinary p squared, which is shown here. Okay, this is just your potential part, but you also get the square of this thing. If you look at it, you'll get the square of that a, which correspond to that. Okay, and you have the cross term, and because this is actually an operator, so you get a contribution in this particular form. You get p dot a plus a dot p, and I have not sort of equate them to be equal, okay, because they are operators. Okay, these are operators. But what one can actually do is the following. When you do, if you look at for example, p dot a, and then you do you do a position representation. So here you're looking at position representation of the operator. So in other words, what we do is to pre-multiply this with some eigenstate of the position. Okay, so that you can see that this so in order to do this, okay, this has to act on some ket. So this is an arbitrary ket. Okay, and then the position representation will be pre-multiplying this with the eigen kets of, well, the dual or eigen ket of position. Okay, so once it does that, this acting on this what I call eigenket of a position, it will give you the necessary form of your momentum operator. Okay, now remember that this momentum operator is not the modified one, it's the ordinary one. So you have the derivative here. So essentially this is given in terms of the vector. So this is really your dash means ddx dash dy dash edz dash. Okay, so that comes in, and then okay, I've forgotten the dot product here. There should be a dot product. Yeah, there should be a dot product. So essentially, you sort of A will be just the divergence. Okay. Right. What one can actually do now essentially to okay, I should be a bit more careful over here. Right, your gradient operator is acting on both this function. Okay, remember when you have an operator, say x over here, acting on, say, sorry, let me do this again. Suppose you have a operator here acting on some wave function which is position representation of the wave function. Okay, so that will just becomes an ordinary function. Okay, so this is just a multiplication operator. So in this way, this becomes just a function now. So you have to, all this what you call, you have to understand the equation by context. So sometimes I think of this as an operator, but when it acts on a function which is a position representation, then it becomes a function. Okay, so so now it acts on two parts. One is this, okay, and the other is this. So you can think of this like as your wave function. Okay, so now what happens is that, okay, there will be a part where it actually acts on this vector potential, okay, and that gives you this. So, and then this will be just your wave function here, and then the other part will be your gradient operator acting on this wave function, and that can be given as this equation here. So you can think of this as a function itself, and then this is the minus IH bar down. Okay, so so you have these two terms coming in, and the essential thing about this is the fact that one gets this term expressible in terms of the different ordering. So remember that this P dot A, we are considering that at the moment, but you also have this A dot P, and A dot P appears also from this action of your gradient onto the whole thing here. Okay, so what can be done over here is, if one has this term to be equal to 0, then essentially your P dot A will be just equals to A dot P. Okay, so this thing is essentially your gauge condition, and you probably have come across this inside your special relativity lectures. This is sometimes called well, I mean, in relativity, it's called the Lorentz gauge, but sometimes it's called the Coulomb gauge. Okay, so you can, provided that you have this gauge condition, so it is sort of fix the gauge in a particular Coulomb gauge, then you can just simply replace the P dot A by A dot P. Okay, so that's the thing that we're going to have over here. And A dot P, now you have to look at the previous expression for A. Okay, remember we had the earlier vector potential that we have sort of defined here. Okay, so you plug this in. Why is it not moving? Okay, plug this in into this, and you're gonna get, well, now you consider this just like ordinary vector, but you can think of it as operator. So you just dot product this thing which involves your B earlier together with P, then you can actually reduce it to this if you do the algebra. And then if you look at this, okay, this corresponds to your Z component of your angular momentum. Okay. The other thing that appears inside your Hamiltonian is this A squared. Okay, so you have to calculate that as well, and your A squared can be reduced in using the same formula for the vector potential. It can be reduced to that. So finally, we rewrite the Hamiltonian as follows. So you have your kinetic energy now, and then your whatever potential there is inside your system, and then the contribution of your magnetic field comes into this term together with this term. Okay, so let's consider adding a further term inside here. So remember that this is coming from orbital angular momentum. So what we're going to do is to add in spin into the system. Okay, so you consider the atom having the electron in the atom having spin, and then this will be a spin magnetic moment interaction with the magnetic field, and this is given by that. Okay, so now essentially you have this Hamiltonian plus that Hamiltonian. Okay. So together all of this can be written as three parts. Okay, so you have essentially the ordinary Hamiltonian, okay, which is just kinetic energy with the potential energy, and then the one coming from the one coming from your magnetic field over here. I've forgotten about the spin orbit, but never mind. So essentially you have this coming from the earlier magnetic field contribution, and then because you introduce spin, then we have to consider like before in the case of your Stark effect, you have to consider, if I'm not mistaken, I can't remember precisely where, but you have to consider the spin orbit interaction. Okay, so you have three parts of the Hamiltonian. This is the unperturbed Hamiltonian, and then you have the contribution from your magnetic field over here, and then your spin orbit. Now there is, okay, I've forgotten about this factor of 2. This comes from the G factor. It's a bit hard for me to explain this without going to further details, but you can consider that G factor sort of modifies the contribution from the uh, spin magnetic moment. Okay. Right. So now what do we do? What we do is to consider the contribution from your magnetic field, okay, as a perturbation. So this will like as is, this is like your perturbing potential, and then your unperturbed Hamiltonian consists of the original Hamiltonian together with the spin orbit. Okay. So just like before, I can't remember precisely where. Just like before, we have two sets of once you consider spin angular momentum and orbital angular momentum, then you should actually combine your two angular momenta to form the total angular momenta, and then you have a choice of what eigencats to choose. Okay, and the one that we are going to choose is going to be the one involving your total angular momentum. Okay. Uh, and what happens in this particular case, one will have to actually see whether you can sort of evaluate your HB in terms of this eigencats of J squared and Jz, and our HB is now written in terms of this angular momenta operators, the Z components, okay. But now since there's a factor of 2 over here, I can combine one of the spin angular momenta here with that orbital angular momenta to form your total angular momentum. Okay, and that leaves just an extra piece which come from the spin angular momentum. So now what happens in this particular case is, from your perturbation theory, if you want to calculate your first order energy shift, you just need to find the expectation value of this HB, okay, with the cats given here correspond to eigencats of H naught plus HLS, which have actually identified this to be your J squared and Jz. Okay. Now this is fine to a certain degree. The only problematic piece over here is coming from your spin. Your Jz over here, if you evaluate this with respect to this eigencats of Jm, okay, so you take your eigencat over here as your Jm here, then your Jz will just simply gives you mh bar. Okay, but how to evaluate sz with respect to this eigencat? Well, over here, there you need to do recall back the idea of addition of angular momenta, and what we need in this particular case to re-express this as combination of your what you call the uncoupled representation, which is in this case you have your ML and your MS. Okay, so so one needs to do that, and essentially that involves the Clebsch-Gordon coefficient. Okay, so you refer back to earlier notes. The thing that we are looking at is essentially this kind of eigencats of your Jm here, okay, where J is precisely either L plus a half or L minus a half, because your spin is just S equals a half, and then your M will be depending on your value over here, okay. And if you remember, we have the condition that you must have your M here, which correspond to the J, must correspond to ML plus MS. Okay, so in this particular case, there are two possibilities. Your ML equals to M minus a half, and then you add up MS equals to a half, so that gives you back so you put this as M minus a half plus MS is a half, so you get back your M. Okay, similarly, either you get this or you get M plus a half minus a half. Okay, so you get that. So it can be written as a combination of these two uncoupled representation. Okay, and then you just need to find out what these Clebsch-Gordon coefficients are, which you can refer back to your notes. So we get this written down in terms of this uncoupled representation. And why this is useful? Because you want to evaluate essentially your Z component of speed. So let's replace this by C plus over here, and then which correspond to the plus over here, and then C minus over here correspond to this minus a half there. Okay, so if you take the expectation value of Sz with respect to this, then you can actually calculate out that this has to be equals to this, the difference between the two magnitude of the two coefficients earlier. Okay, and just writing out the coefficients now. Okay, this, remember, this is a modular square, so I have a square it here, so I have a you have to square that, and there's a common factor here given by 2L plus 1. Okay, so that brings, you can bring it out. So what's left is the numerator, which is correspond to that coming from here, and this one coming from here. Okay, so you can actually combine them algebraically, so that will cancel off your L and your half, but it combines your M together to give you this. Okay, so finally, since we have now calculated, so this is actually your GM thing. Okay, so essentially we have now calculated both, because the first part gives you this value. It's just this part that we have not determined what it is, but now we have done that. So you combine these two, and then basically that gives you the first order shift in energy due to the magnetic field. Okay, and okay, what else over here? Okay, so one of the things that's going to be important for us is that you can see that this shift is actually proportional to this M. Okay, what's M? M is the eigenvalue of your Jz. So somehow there's this this m is coming from jz, so somehow the thing has been projected in the z component of your total angular momentum. So one could actually prove this using projection theorem. Okay, this is from earlier notes. So where you have your vector operator here being evaluated between two angular momentum states. Okay, what happens is that one can remove the dependence on your m and m dash. This is your Wigner-Eckhart theorem, but now specific to this projection thing. Okay, so you have that, and then essentially this will give you the part where it depends on m and m dash. So this part independent of m and m dash, and this part depends on m and m dash. Okay, so we can use this projection theorem to this particular result that we had earlier. When you do that, essentially VQ here is going to be replaced by SZ, and remember the SZ essentially correspond to the Q equals 0 component. Okay, you recall back for your spherical tensor thing. So, and this VQ is V naught, and J dot V will just give you this S dot J. Okay. And this part, okay, this correspond to that, and this part is the one that we have evaluated earlier. Sorry, no. This part is evaluating your SZ, okay, between JM and JM dash, okay, and this you know how to no, it's not SZ, sorry, this is JZ. Z. Okay. So this gives you JM dash JZ JM, and JZ JM essentially MH bar JM. Okay. So that gives you this part. Okay, and this one is just you just put it underneath here. Okay, so now our problem is just to find out what this is, which is coming from that J dot V there. But you can get cross terms like this by expanding your J squared, and then you subtract the necessary part, which is in this case is your L squared here, and that will actually give you the cross term S dot J. Okay, so we'll do that. So in other words, what we have over here, and also remember when you do the cross term, you have a factor of 2. So the factor of 2 comes over here. So you get J squared plus S squared minus L squared evaluated at this eigencat. Okay, but you know how to do this. Okay. So this gives you your J squared will give you J plus 1, okay, which is that. Your S squared is simply half plus 1, and your L squared is simply L plus 1. Okay. So the same thing over here, your J will be replaced by L plus or minus half. Okay. and you can sort of simplify this, and then you get back to the original expression that we had. So in other words, that's the reason why this factor of m appears inside your energy shift. Okay, so what we have done so far is to consider, where was it? We consider HB as perturbation to that. So in other words, the assumption here, your contribution of your HB is small. Okay. So if you look at what is HB, we require that this B is small. Okay. So we want to do the case where your B is no longer small. Okay. Instead you have a strong B. Okay. So here is the case of B being strong. So B is significantly large, and what we need to do is now, instead of HB perturbs H naught plus HLS, what we do is now HLS perturbs H naught plus HB. Okay. So again, in order for us to calculate your first order energy shift, what we need is to find a common eigenket for this both H0 and HB, and this is just your uncoupled what you call representation of your angular momentum. Okay. So once you do that, you can actually see, okay, I can evaluate your HB. Okay, remember your HB is given by that. So if I have the uncoupled case, I know how to evaluate this, I know how to evaluate that. So that gives us, where was it? That gives you your ML. Remember that this is LZ plus 2SZ. Okay, that will be your MLH bar here, and then 2MSH bar here. Okay, and then you have the other factors appearing in the Hamiltonian. Okay, so we know how to do that. So that settled this problem. So the other thing that we need to do now is how to calculate that first order energy shift from the spin orbit perturbation thing. Okay. Well, that means I need to do something like this. So I have this. Remember, we have your ML, MS, your uncoupled thing. So we need to find out what's the expectation value of that. Okay. So this is essentially the thing that we have. But L dot S, you remember L dot S is just your LX SX, LY SY, plus LZ SZ. But you can rewrite this as half of L plus L minus plus L minus L plus to get this particular two terms, and then you just leave your LZ and SZ, which is when it acts on these eigenkets, you know what the value is supposed to be. What about the L plus and L minus? Well, once you have these ladder operators, for example, you know that L minus M, say ML here, will be proportional to ML minus 1. Okay, and when you do this, you will find that the contribution from there you will get essentially equals to 0. and similarly for your S plus and S minus. Okay, so in other words, the contribution here is 0, and all you need to do is to evaluate the LZ and SZ operator acting on this particular case. Okay. And finally, that gives you this, okay, ML H bar times MS H bar, and then you just plug this back into your HLS, which is given earlier. Okay, so one needs to evaluate this as well, but we leave that for no. It's just we just want to get the expression in terms of the no, I mean in terms of the expectation value of your L dot S over here. Okay, so we have two things that we have done so far. So the first part is to have the case of a weak magnetic field, and then what do? You do evaluation with respect to your J squared. Yeah, okay, sorry. This is meant to do this. So you use that. No, okay, this is right. So that J squared, essentially what you do, you use the couple representation for the first case. And then for the second case, the strong magnetic field, use the uncoupled representation. Okay. Right. Now you might want to see what precisely is actually happening when let's suppose you do an experiment where you do sort of vary the magnetic field. Okay, so then essentially you go from the weak magnetic field to the strong magnetic field, and you want to see what actually happens towards the states. Okay, so and for our particular case, we are going to look at the state of P shell, which is correspond to L equals to 1. Okay, so in the first case we have seen earlier, when you have a weak magnetic field, you get this result. Okay, so if I consider this as your variable here, so your B is going to be varied. Okay, and what's going to happen, you're going to get this as a slope. Okay, so you get this particular slope multiplying your B. Okay, and this will be contrasted with the case of the strong case, where your expectation value of your HB is now given by this. So here again we treat your B as a variable. So what would be the slope, more or less, and you can see that it corresponds to this, is proportional to this ML plus to MS. So how does it go from one case to the other? Is the fact that one looks at the case of your HB. Your HB is essentially having those operators here, and this operator is a spherical tensor. Okay, and what do you know about spherical tensor? No, when you have a spherical tensor over here, okay, the essentially there is a relationship that you need to obey between your your, I should put in J dash here. The relationship, you probably remember that this has to be equals to M plus Q, and then your J and J dash will be related via this rank operator. Okay, so what's going to happen in this particular case is that uh, there's a tendency to mix up different M's. Okay, so in this case you have two possibilities where you have your total M to be equals to see, yeah, your total M equals to M equals to plus or minus a half, but your spin and your L, your Z component, your spin, and your Z component, your L, contributes in terms of 3 halves and a half. Okay, so the total one is the same, but this one are two different things. So you mix up those two things when you do uh, this kind of interaction over here. Okay. So in other words, what happens in the end, the two different states gets mixed up, and finally you come down to the fact that you have the strong energy limit. Okay. So in between the shift that we found earlier, the one with the dollar sign here, this one, this shift, and the other shift for the strong case is given, where is it? This one. Okay. In between they will not work. Okay, so when you do this transition from the weak limit to the strong limit, it will be something different, for which your perturbing matrix potential, okay, will not be diagonal in that particular case, and then you need to do all this diagonalization. Okay, in the book by Sakurai, it refers to a particular paper, I can't remember by whom, that you can actually do this. Okay. The next one is probably we want to apply to perturbation theory to van der Waals force. Okay. So essentially, remember in probably at this first year physics or high school physics, you learn about van der Waals force is some kind of effective force between two atoms. So in this case, we're considering the case of two hydrogen atoms in this manner. So you have your nucleus here, and then your electron here, nucleus here, electron here. And then one can write down the Hamiltonian for this. Okay, so you have your Hamiltonian. This is just the Hamiltonian of your two individual hydrogen atoms. Okay, this one plus that correspond to the first hydrogen atom. This one plus that correspond to the second hydrogen atom. But you have the other potentials coming in. Let me just think of it a little bit. You should have between this nucleus with that gives you that, and then you have I think which is which, R minus R2 will probably be this one and that, and then this one and that. Okay, so you just need to figure out in terms of the vectors given inside this figure. Okay, so you get this extra perturbation potential, for which one has to figure out how to actually simplify this. Now okay, let me just move on. So the unperturbed Hamiltonian here is just your it's just your Hamiltonian of individual hydrogen atoms added up. Okay. So if I were to find the unperturbed states, I will just use the unperturbed states of the individual hydrogen atom. So here I can think of your ground state, for example, for one hydrogen atom here for the first one, and then another hydrogen atom, uh, the ground state also over here. Okay, so one needs to add this perturbing potential, but this is too complicated for us to do. We need some kind of approximation. Here the assumption over here is that this R between the two atoms over here is going to be large, at least larger than the Bohr radius. Okay, so with respect to that, one can actually expand your potential in terms of this. I've yet to prove this properly, but perhaps I can do this later on, or I will modify the notes to include the details. Okay, so essentially one can simplify in terms of this approximation here. Simplify your perturbing potential is given by that. Okay, so now what we do is again we calculate your first order energy shift, and for the first order energy shift you find that this matrix element seems to give you a 0, simply because in that case you have your L equals 0, and then you'll be able to show that using integral over your spherical harmonics. Okay, for L equals 0 case it gives you just a 0 expectation value. So one needs to go to the second order perturbation theory, and you can see that my notes is not finished here, so I'll just go to the book. I want to finish off this part of the chapter here. So one has in the end to go to the second order perturbation theory. So you remember the second order perturbation theory will involve something like this on the denominator, showing from the ground state energy minus some excited state energy. So in other words, there will be a contribution coming from the different levels of the energy states. Okay, so that essentially coming from the second order perturbation term, but the main thing that one gets over here is this thing. Okay, you get this 1 over R6 what you call 1 over R6 dependence. Okay, and this is the thing that we have claimed earlier inside over here. Okay, the other part that was claimed is the fact that it's attractive. One can also get that because your second order perturbation term involving this E naught, your ground state energy minus the higher state energy, and of course you know that this is going to give you a negative sign. Okay, and that shows that okay the shift is going to be shift towards the attractive part rather than the negative part, positive part. Sorry. So that sort of settles this part, and then the next thing that we're going to do is we're going to look at variational methods, and then after that only we go into the time dependent perturbation theory. Okay, so I think I'll finish off this today. So let me take the attendance. So the other thing that I should mention is your assignment. So could you hand it in by when do you want it to hand it in? I've yet to create the folder though.
Convenient for you.
Okay, so if you want, I can no, maybe before 5 p.m. Is that okay? Or if you want to extend it, just let me know. Okay. So I think that's all for today. Thank you, everyone.